All right, away we go. So today we're going to start with what's called implicit differentiation. We're going to go to the same example we did yesterday, where we took a relation, right, not a function, because it does not actually pass the vertical line test. For every x, there is not a unique y. Like, for example, when x is 9, y could be 12 or negative 12. So we took yesterday this circle example, and we rearranged the equation so that it was explicitly defined as y. We turned it into y equals, which is what we're a lot more used to looking at. We actually kind of turned it into two functions. Y equals positive 225 minus x squared, and y equals negative the square root of 225 minus x squared. So we're going to today not do that. We're going to not define y explicitly as a function of x. We're just going to assume that the derivative exists. In other words, we're going to implicitly assume y is a function of x. So we're going to take the derivative with respect to x of the entire function. Sorry, relation. So we're going to take the derivative of the entire thing. Excuse me, both sides of the equation. All right, the derivative of x squared we've done enough times. We know that's 2x. But how do we find the derivative with respect to x of y squared? Well, I'll just show you how it looks. You basically treat this like a chain rule. So it's 2 times y times the derivative of y with respect to x. Now here's the thing, I don't really know what y is with respect to x because I didn't bother to rearrange this thing so that it's y in terms of x. So I'm just going to leave that there because at the end of the day, this is what I want. So again, think of this as chain rule, right? The exponent, give me a highlighter here. The exponent became my coefficient, and then I left the thing that I'm taking the exponent to, the base, alone, and then I found the derivative of what was inside that base. Same way that you do chain rule. The other side of the equation is easy, the derivative of any constant 0, no matter how big it is. And my goal now is to isolate dy by dx, which of course is the slope that I'm looking for. So what I do is I take this equation, which right now says 2x plus 2y times dy dx equals 0, and I solve it for dy dx because at the end of the day, dy dx is what I'm looking for, right? It's the change in y divided by the change in x. It's the slope of the curve. So you would think of this thing like it's an operation, but suddenly I've turned it into a variable. It's like it's changed roles on me. I compare this to the way your generation likes to just sort of play fast and loose with nouns and verbs. It weirds out us old people, but it's definitely the way you folks talk. Right? You'll say things like, I don't feel like adulting today, or I forgot how to math. It's like, you take a word that's perfectly good as a noun and you just turn it into a verb. You can't math. Math isn't a verb in and of itself, but that's the way you do it. You just sort of say, I'll use this word as a verb even though it's a noun. Same idea here. This is an operation. It's a, right, find the change in y and express it as a ratio by the change in x. I'm just going to say, no, this is my new variable, and I'm going to rearrange the equation for that variable. So the 2x moves to the other side by subtraction, and then I divide both sides of the equation, and then I simplify it. All right, and then we'll stop there for O Canada.
Please stand and remove your hats for O Canada and the treaty acknowledgement.
Okay, we're live again. So you might be looking at this and thinking about the example we did yesterday and going, how can this tiny little thing be the slope of this circle? Because yesterday, the slope of the circle looked like this. Let's go back to the example yesterday. When we took the time to rewrite the equation, did our calculus, we got this, which doesn't look anything like the very nice little simple negative y over x. But remember that this thing represents the slope of this function, which is only half of the circle. One of the advantages that very often happens when you do it the implicit differentiation way is you get a simpler expression. And I can kind of show you that this, in fact, is going to work out the same, because when I finish off today's example here, remember I was supposed to, if you go back to the question, I was supposed to find the slope of the tangent at the point 912, which is the same thing we did yesterday, and we got negative 3/4, and that's what we're going to get today. If I have to do this at the point 912, then I'm doing dy by dx when at the point 912, which means x will be negative 9, y will be 12, and I get the same slope that I got yesterday from the much bigger looking version of the slope, or at least much more complicated function representation of the slope. Implicitly defined, it actually worked out to be way easier to work with. Okay, this is the part that people find odd. This whole, yeah, but what do you do with this y? Let me point out to you that this shouldn't be entirely a new idea to you. When I hit that part of the question, the derivative of, with respect to x of y squared, you think of it as the chain rule. So the derivative with respect to x of y squared is like finding the derivative of y squared with respect to the x, knowing that y is equal to some rule with x. I just don't happen to know what it is. It's kind of like when we did the Leibniz notation for chain rule, right? When we say, we know that, just like we say we have the function y is equal to x squared plus 2 all squared. Well, I could represent this x squared plus 2 as just u. So I can think of this as y equals u squared and u equals x squared plus 2. And then using our Leibniz notation, the derivative of y with respect to x is the derivative of y with respect to u times the derivative of u with respect to x. Or outer function, inner function, which is kind of the way I thought about it the first time I looked at chain rule. So when I'm doing something like that, the derivative of, with respect to x, of y squared is the outer function times the inner functions. And that's going to be 2y. And then this becomes an unknown. So again, I treat this as a variable. And again, to me, this is similar to sort of a Leibniz example of chain rule. Like, for example, one like this. Suppose I had y equals x squared plus 3 to the power of 6, right? Well, doing this the Leibniz way, we replace x squared plus 3 with u, and then I think of this as y equals u to the 6, where u is equal to x squared plus 3, and then the derivative of y with respect to x is the derivative of y with respect to u times the derivative of u with respect to x. And of course, this part is kind of the easy part. It's just the derivative of that, which is 6u to the 5. But the way we've been doing, the way we'll be doing implicit differentiation, I should say, is that this part will remain an unknown. And it'll be the thing that we solve for. Whereas, say that I know this part here will be some sort of constant that'll probably just go away. I'll just leave it. Okay, so that's the way we do implicit differentiation. Just as a kind of a quick practice, So we've already seen this one. The derivative with respect to x of y squared would be 2y times dy dx. What if it was just plain the derivative with respect to x of y? What if it didn't have a squared or on it? Well, then it would, think about it, it would just be dy by dx. If you really want to think about it, I'm doing this the same way I did this one, right? This 2 becomes my new coefficient. So this, remember, y means y to the power of 1, right? So this 1 becomes my new coefficient. And then y squared becomes y to the 2 minus 1. So in this case, I'd have y to the 1, which would be y to the 0 when I'm done doing the derivative of it, and then times dy by dx, and you can see how this simplifies to that. What if, however, it's a factor in a bigger term? Then I think about it using product law, or product rule, I should say. So how does product rule work again? Well, it's the derivative of the first thing times the second plus the first thing times the derivative of the second, and the derivative of y squared is, well, like it says here, 2y times dy by dx. Let's try this one. Derivative of x cubed y is, again, product law. I think of this as x cubed times y. So it's the derivative of the first thing times the second thing plus the first thing times the derivative of the second thing. So with this new skill, we no longer have to worry about rearranging a big relation and isolating it into y equals. And that's a good thing, because in the circle that wasn't very hard. We just had to deal with that whole, well, there's a plus square root side and a minus square root side. But it wasn't all that hard to rearrange it. That was basic algebra. You could have done that in grade 8. But check out this dude. Any idea how you would strategize isolating that y? I mean, you could think, well, okay, I can move the x squared to the other side, and all the y's are on one side. And then I could try factoring y out of these two terms, but then one of them still has y to the 5 in it. How would I get those y's completely isolated from x? And the answer is, there kind of really isn't a way. This is a little off the scope of this course, but in grade 11, of course, you learned that there's a quadratic formula. Any equation that has an x squared as its highest degree is solvable if it solves, right? If there's no solution, there's no solution. But the quadratic equation will get you any solution that might exist. It'll even get you the imaginary and complex number solutions if you really want to play with it. Is there such a thing as a cubic formula that can solve any cubic equation? Yes. We don't teach it because Google it. It's big and oogly. And pack a lunch if you want to see the quartic formula. There is one, but unless you want to program a computer to do it, you'd sit there and to do one example would take you probably hours of paper and pencil calculation, but it does exist. There is no actual quintic formula. That's the actual first degree number, that there is no specific algebra way that you can algorithmically solve every quintic equation. You can for powers of 4, powers of 3, and of course in grade 11 you learned for powers of 2. So this is a good example that I actually asked Mr. Lack when he picked this example, did you pick one that works out that if you tried to factor it out you'd get a y to the power of 5? Because that is completely unsolvable. There is no algebra trick. There's no tool that you could find for your algebra toolbox that would isolate this variable. And he said, no, I just happened to grab that one. I said, well, that was very fortuitous that you picked one like that then. Because this one really, without implicit differentiation, isn't going anywhere. But with implicit differentiation, again, I think I'm going to do the derivative of this entire relation. And as long as I know my chain rule and my product rule, it's actually not that hard. Okay, so chain rule says we're going to do the derivative of this thing. And this is product rule, right? Sorry, I should have said product rule, not chain rule. Product rule of this thing says we're going to do the derivative of the first times the second. Oh, I forgot the squared. Thank you. Plus the first times the derivative of the second. Now we'll move on to deriving this guy. That one's easy. That's just 2x. Then we'll move on to deriving this guy, which again I think of as a chain rule. So it's the outer derivative, which is 6 times 5, and then y becomes to the power 5, times the inner derivative. And of course, the derivative of any constant, I don't care how big it is still 0. And remember, what I wanted to do is I wanted to find a derivative. I wanted an actual equation that represents the slope anywhere I want along this wacky curve. And as long as I can isolate for this thing, treat it as a variable, that's what my expression will represent. It'll represent the slope everywhere along this big thing. So now that we're in this form, how do I solve for this? Well, the way you do all algebra, you try to isolate it, right? So the x cubed dy by dx plus 30y to the 5 dy by dx is equal to, and then I'm going to move these two things that don't have that factor that I'm looking for to the other side of the equation. They, of course, become their opposites, right, because you subtracted them from both sides. Any idea what you're going to do next? Remember, the goal is to isolate this. Problem is, it's in two different terms. It'd be nice if I could add these terms together, but they're not like terms. So what tool from my toolbox is going to help me here? Any ideas? Getting a lot of blank stares this morning. It's feeling like a long week, isn't it? Yeah. We good? Anybody? Any ideas? Guys at home want to play? What's my next step here if my goal is to isolate this thing? You can factor it. If I factor this factor out of those two terms, now it looks like this. And then I have one more step. Divide both sides of the equation by this factor. Some people still call this cross-multiplying. Okay, that's the way you want to think about it. And that would be my answer. This rather complicated looking expression on the right-hand side is the slope everywhere along that curve. I just need to know a point on that curve and plug in its x and its y coordinates, and I can give you a value for that slope. Question?
I think you forgot a y.
Where did I lose my y? Hey, thank you for being more awake than me. Okay. And I have a question in the chat that says 1 centimeter. What? I have no idea what you're trying to tell me. Okay. Probably had to do with that y that was missing. Just for fun, what if I asked you a question like, okay, look at this thing. It's this very kind of wonky, curvy thing. What if I asked you a question, maybe add this to the question. Now we could answer something like, where is this curve, where is this curve's horizontal tangent? Okay, so where is this curve's horizontal tangent? Any ideas? Well, let's see. We could say, well, tangents are horizontal when the slope is equal to 0. So if we set this slope to be 0, I don't really care how complicated that denominator is, because when I times both sides of the equation by that denominator, I get 0 equals negative 3x squared minus 2. Oh, look at that, I forgot the y again. Y minus 2x. And then I could start, now this would still be kind of complicated because I have an xy equation here. But I could try solving it. I could try, first of all, I don't like all these negatives, so I think I'd multiply both sides of the equation by negative 1. And then I could try, well, once again, I'd probably just leave it there and maybe start guessing and checking some values or graph this. So I would say for all x comma y in this expression, or maybe not in this expression. How about for all x comma y that satisfy this expression, the slope would equal 0. So there you go. So that's the kind of math you can do with things like this. Okay? All right, I think we'll stop there. We'll save example 3 for tomorrow. I'll stop my little lesson, so we'll continue this lesson tomorrow and finish it off. Okay.